The paradox of power before electricity. Walk into any industrial museum displaying 19th century machinery, and you're immediately struck by a paradox. Massive mechanical looms, towering forge hammers, rotating saws, and hydraulic presses dominate the floor. Machines weighing tons, moving with precision, operating continuously. Yet there are no electric motors, no wiring, no generators, no control panels. To the modern observer, this seems almost impossible. An information plaque may casually mention steam-powered or water-powered, but that explanation barely scratches the surface. The truth is far more complex and far more impressive. These machines did not merely use power, they were part of an integrated mechanical ecosystem designed with extraordinary ingenuity. The fundamental question historians often gloss over is this: how was energy generated, transmitted, regulated, and distributed across entire factories without electricity? The answer reveals an engineering tradition so refined that it rivals modern systems in creativity, if not efficiency. To understand it, we must return to the middle of the 19th century, when industrial civilization was accelerating rapidly but electricity had not yet entered practical use. Factories could not rely on individual motors. Every machine had to be powered from a single source. That meant energy had to be generated centrally and distributed mechanically, through rotating shafts, belts, gears, and flywheels. Imagine a textile mill in Lancashire around 1850. A 5-story brick structure filled with looms, spinning frames, carding machines, and presses. Hundreds of moving parts. Thousands of pounds of iron in motion. All synchronized. There were no outlets to plug into. Instead, the entire building functioned like a single organism. Its heart was a prime mover, usually a steam engine or water wheel, producing rotational energy. That rotation was transmitted through an intricate network of shafts running the length of the building, branching upward through floors, distributing motion to each machine. This system required precision alignment, constant maintenance, and a deep understanding of mechanical physics. The slightest miscalculation could lead to vibration, excessive wear, or catastrophic failure. And yet, these systems ran reliably for decades. What makes this even more remarkable is that most of the foundational technologies, bearings, gears, governors, belt systems, were developed without computers, simulations, or modern metallurgy. Everything was designed through experience, mathematics, and observation. This was not primitive engineering. It was mature mechanical science. Understanding how this worked requires breaking the system down into its fundamental components: power generation, transmission, regulation, and storage. Each of these was solved independently long before electricity entered the picture, and once you see how it all fit together, it becomes clear that the Industrial Revolution was not powered by steam alone. It was powered by human ingenuity applied with extraordinary discipline. Centralized power. The steam engine and its role at the center of most 19th century industrial facilities stood the steam engine, a machine that converted heat into motion with remarkable effectiveness for its time. But, contrary to popular imagination, steam engines were not crude devices. By the mid-1800s, they were sophisticated machines refined through over a century of development, beginning with early atmospheric engines and culminating in the highly efficient designs of James Watt and his successors. A typical factory engine was housed in a dedicated engine room, often separated from the main workspaces for safety and vibration control. The heart of the system was the boiler, a large riveted iron vessel where water was heated by burning coal. As water turned into steam, pressure built up. That pressurized steam was directed into a cylinder where it pushed a piston back and forth. This linear motion was then converted into rotational motion through a crankshaft and connecting rod, the same basic principle used in modern internal combustion engines. But the real genius of the steam engine lay in its regulation. The steam did not flow continuously. It was precisely timed using slide valves that opened and closed in synchronization with the piston's movement. Exhaust steam was released after each stroke, preventing pressure buildup and allowing the next cycle to begin to regulate speed. Engineers employed one of the most elegant mechanical devices ever invented. The centrifugal governor. Two metal spheres mounted on rotating arms spun as the engine ran. As speed increased, centrifugal force pushed the spheres outward and upward. This motion was linked mechanically to a valve controlling steam input. Faster rotation closed the valve slightly, slower rotation opened it. The result was automatic speed regulation, a feedback control system operating purely on physics, no electronics required. This allowed steam engines to maintain remarkably stable output even as loads changed throughout the factory. Large factory engines produced anywhere from 50 to 200 horsepower. Their flywheels, often several meters in diameter and weighing up to 20 tons, stored rotational energy, smoothing fluctuations and allowing machines to run evenly. These engines were not set-and-forget machines. They required constant monitoring. Engineers checked pressure, lubricated bearings, cleaned valves, and inspected for leaks. Boiler explosions were a real danger, which led to the development of pressure gauges, safety valves, and early industrial safety regulations. Despite their inefficiency by modern standards, often converting only 10 to 15% of fuel energy into mechanical work, steam engines represented an enormous leap forward compared to animal or human labor. More importantly, they freed factories from geography. No longer tied to rivers or wind, factories could be built wherever coal and labor were available. This single development reshaped cities, transportation, and global economics. But generating power was only the beginning. The real challenge was transmitting that power across an entire factory. Line shafts, belts, and mechanical power distribution. Once power was generated, it had to be delivered, not to one machine but to hundreds. This was accomplished through a system known as line shaft transmission, one of the most impressive mechanical networks ever devised. At the core of the system was the main shaft, a long solid iron or steel rod running the length of the building. It rotated continuously, driven directly by the steam engine or water wheel. From this main shaft, secondary shafts branched off vertically and horizontally, distributing motion to every floor. These shafts were supported by bearings mounted to beams or ceilings, spaced every few meters to prevent sagging or vibration. The shafts themselves were massive, often 20 to 30 centimeters in diameter, and had to be precisely aligned. Even slight misalignment could cause oscillation, friction, or catastrophic failure. Power transfer from shaft to machine occurred via leather belts and pulleys. Each machine had a pulley connected to its drive shaft. A belt looped around this pulley and around a corresponding pulley on the line shaft. When the belt was engaged, the machine ran. When disengaged, it stopped. Speed control was achieved through pulley size. A small pulley driving a large one reduced speed and increased torque. A large pulley driving a small one increased speed. Operators could engage or disengage machines without stopping the entire system by shifting belts between fixed and loose pulleys. This required skill. A mistimed shift could snap a belt or damage equipment. Belts themselves were marvels of craftsmanship. Made from layered leather, stitched or riveted together, they had to maintain perfect tension. Too loose and they slipped. Too tight and they wore out bearings. Maintenance was constant. Belts were cleaned, oiled, adjusted, and replaced regularly. Bearings were lubricated daily. Dust and debris had to be cleared to prevent overheating. Despite the complexity, the system worked, and worked reliably. Factories ran for decades using nothing but rotating shafts, belts, and human attention. Water power and hydraulic engineering. Before steam dominated industry, water was king. Water wheels had been used for centuries, but the 19th century saw them refined into highly efficient industrial machines. 3 primary types existed. Overshot wheels, where water entered from above, using gravity for maximum efficiency. Breast wheels, where water struck at mid-height. To undershot wheels, driven by flowing water from below. Overshot wheels were the most efficient, converting up to 80% of water energy into mechanical motion. Some reached diameters of 15 to 20 meters and produced tens of horsepower. Water was delivered via carefully engineered canals, sluice gates, and reservoirs. Flow could be adjusted precisely to control speed and torque. The wheel's slow rotation, often only 5 to 15 revolutions per minute, required gearing to increase speed for machinery. This was done using large wooden or iron gears, often with replaceable wooden teeth. Water power had advantages. It was free, continuous, and clean. But it also had limitations. Drought reduced output. Freezing halted operation. Flooding caused damage. Many factories therefore used hybrid systems, combining water wheels with steam engines to ensure reliability. In mountainous regions, gravity-fed systems reached extraordinary sophistication. In flatter regions, windmills or animal-driven mechanisms filled the gap. Each region adapted to its environment, resulting in a remarkable diversity of mechanical solutions. Precision craftsmanship without modern tools. One of the most astonishing aspects of 19th century machinery is the precision achieved without modern tools. Gears were cut by hand using dividing plates that ensured exact spacing. Shafts were machined on lathes driven by the very systems they helped create. Bearings were hand-fitted to tolerances of fractions of a millimeter. Flywheels were balanced manually by observing their rotation and removing or adding material until equilibrium was achieved. Everything depended on skilled labor. Engineers learned through apprenticeships, not textbooks. Knowledge was passed through practice, observation, and experience. Failures were studied carefully. Improvements were incremental but relentless. This craftsmanship allowed machines to run for decades, some for over a century, with proper maintenance. Flywheels, governors, and mechanical stability flywheels were the stabilizers of the entire system. By storing rotational energy, they smoothed out fluctuations caused by piston strokes or load changes. Their mass, often concentrated at the rim, provided inertia that kept machines running smoothly. The interaction between flywheel and governor created one of the earliest feedback control systems in history. If speed dropped, the governor opened the steam valve. If speed increased, it closed it. This dynamic equilibrium maintained consistent operation long before electronic control systems existed. The engineering principles involved, inertia, momentum, feedback, are still taught in mechanical engineering today. A world built on motion, not electricity. By the late 19th century, factories across Europe and North America operated as enormous mechanical organisms. Power flowed through shafts like blood through arteries. Flywheels acted as hearts. Belts served as muscles. Governors functioned as nervous systems. Everything moved. Everything depended on balance. Everything required human understanding. When electricity eventually replaced these systems, it did not do so because mechanical power had failed, but because electrical distribution was more flexible, safer, and scalable. Yet the foundations of modern industry were laid by these earlier machines. They prove something important. Advanced technology does not require electronics. It requires understanding. And the engineers of the 19th century understood motion, force, and energy at a level that still commands respect today.